Okay, the first problem that we are doing is problem number 68. And that was the one about the flagpole. You had a 6-foot tall person was walking toward a flagpole or walking away from a flagpole, and you got two different pictures that you're drawing. So the first thing I did when I drew this, first thing I did when I drew this is I drew the entire picture right here. Here's a flagpole. Here's a person. The little squiggly lines mean shadow. Okay? I quickly saw that there's really two triangles there. Do you guys notice that? There's a triangle with the person and their shadow and the pole and its shadow. So I then went over here and I drew two separate triangles, and that made it a little bit easier for me to see. Okay, was there anything in that that made you a little uncomfortable with the wording or something of that problem? Did you understand what they meant while you were walking? It was a little, to me, it was a little confusing reading that problem as to what was going on. Okay, did you start drawing it? How many of you drew something like this? Okay, did that help you once you drew it as to kind of what was going on? All right, I think that will be the thing that you're going to have to try to do, is draw it, and sometimes your drawing will not make sense, and you don't see a triangle there or anything. Then you redraw it. Now, I drew this looking at it this way. In engineering, that would be called a side view. All right, there's another problem in here in a little ways where you're best off doing a top view, like you're a satellite looking down on something. Okay, so this one, a side view, and making it to where you had just two dimensions going on was the key. Another thing that I think messes a lot of people up is, what do you mean where the sun is and the angle of the sun and all of that? Well, if your sun is here, then right there is where the shadow will be. Okay, if the sun was up here, then your shadow would be like here. Okay, so there's two words that they use a lot of times in these, and I saw it, they used it in a few different things. Angle of depression and angle of elevation. All right, angle of depression means you're starting here and you're going down. Angle of elevation, you're starting here and looking up. So the angle of elevation would be this angle right here. Angle of depression would be the angle from the horizontal going down. So if I said an angle of elevation, if I have, here's the sun. I don't think it comes up on this problem, but in later problems it does. And I look at an angle of elevation. I'm talking about somebody from the ground looking up at the sun. And so my angle of elevation is that angle right there. Okay, so it's how you had to elevate your eyes. So you go from your horizontal, looking straight out, elevate your eyes. Okay, angle of depression, this would be instead of maybe the sun, maybe it's a light that you have in a theater classroom, and you're going to take it and move it down. Let's pretend that. Okay. So this would be the other angle, right here. Can you buy that the angle of depression is equal to the angle of elevation? Can you buy that that's true?
Yes.
What's the geometry thing that says that that's true? Remember about these? This is parallel with that. And here's your transversal. What are these two angles called?
I know that's it. The what?
They have two words. One means opposite. The other one means inside.
Oh, it's. Oh, God. I know what it is.
You know what it is. You're forgetting the words. The word is alternate interior. Yes, alternate interior angles are always. If you have two parallel lines cut by a transversal, the alternate interior angles are congruent. Okay, we're going to use some of those facts for doing this, where maybe we're given this, but we really want this because that's where our triangle is. Okay, so sketching it out is one thing you need to make sure you do. And then two, you need to see if there's any congruent angles because of that type of relationship. Also, you might be given this, but what you really want is this one. All right, well, think about that with the 90-degree angle. You can just subtract and get that value. Okay, so sketching it out is going to be very, very important with doing these and seeing if there's some sort of relationship. Alternate interiors is going to come up a lot because they'll give you angle of depression and you need to see angle of elevation. Kind of makes sense word problem wise. Think about if somebody is up on a mountain and or let's say a cliff, and they're looking down at somebody. For your eyes to meet, they have to look down the same way you have to look up, right? Their head going down has to match your head going up for your eyes to meet. So if you kind of have that picture in your head, that's another way you can think about alternate interior angles and how the angle of depression, angle of elevation meaning the same thing. Okay, so we had here two different triangles, and what we're trying to find is a flagpole. So I took this setting, here's the flagpole, here's the person, and after I drew the picture first, I then started putting in the numbers. It got too confusing here, so I broke it out as the two separate triangles. Notice though that that angle and that angle are the same angle. So I can do this one and get what the tangent is. And if I know the tangent, I can put it in the calculator and figure out what the angle is. Correct? All right. So if I know what the angle is, I can then just say the tangent of that angle has to equal x over 135. And then I realized I didn't really need to know what the angle was. Okay, so I could just say 2 equals that. Now, if we were back in geometry before we even learned trig, we could have solved this with similar triangles, right? The ratios have to be the same. So this is to x, so 6 is to x, as 3 is to 135. And you could have just set up a ratio and had this equal to that, and you would have been done.
Where is the 2 coming from? 6 over 2.
That should have been over 3. And notice I solved it correct there, but I put a 2 there. So I knew what the answer was going. I do that sometimes. My brain goes ahead of what I'm supposed to do. So this was a 2, and it's because that was supposed to be a 3. Okay? Anybody get that one? Anybody get 270? Nice, nice. All right. Okay. If you didn't use similar triangles here, and you actually tried to find theta by looking in the chart, then you might be a little bit off with rounding and stuff like that. Okay, number 69. Angle of elevation. So you're skiing down a mountain with a vertical height, and they give you a vertical height, the distance from the top of the mountain to the base, and they want to know the angle of elevation from the base to the top of the mountain. Be very careful when you read these things. When they say the angle from, make sure you get the words of what they want. They want from the base of the mountain to the top of the mountain. So they're wanting that angle. I've had a lot of times in the past where kids calculated everything correctly, but they gave me that angle instead of that angle. All right, so you get some points off because you didn't read it correctly and calculate the angle I want. Now, it would be no problem to calculate the other one, right? I mean, it's 90 minus the one you have. All right, so if that's the angle, we have opposite, and that's the hypotenuse, and that would be a pretty scary slope, I would say. 30 degrees down. Not quite as bad as some I've seen. I don't know, I've never been skiing, so I don't know. If you watch the Olympics, though, I swear they're going like 60 degrees downhill. That's some crazy things they do in the alpine skiing events. All right, anybody get this one? Nice. This one wasn't too bad, I think. Nice, okay. And it was an odd, so you guys couldn't have looked in the back of the book to get an answer. So if you got this one, that was good. And they didn't give you the picture. You actually had to draw the picture for this one. All right, so did any of you say 60 degrees? You got this one instead? Okay, so you just have to make sure you get the angle they want. All right, 70, they gave you the picture, and they kind of sketched in everything. So on my paper, I just kind of redrew the pertinence part, and I have the width and length and angle, and I should always put degree here so we know it's degree instead of radian. Okay, so I just punched it in the calculator now instead of using the table. So either way you do it, it's somewhere around here, and you should get somewhere around that many feet wide. And you go back and look at the picture, and it's probably not drawn to scale, although that one looks like it probably is, and it makes sense to me from their picture that would be 137.6. Yes.
Can I do the problem? Because I put 75 instead of 100 throughout the whole thing.
You did 75.
It's like instead of 100, I used 75.
Oh,
but I don't know why.
and yeah, okay, yeah. So you basically got it right. You knew the method. Well, I don't know why you used 75.
I don't need it.
Okay, you just read it. Yeah.
I guess I was.
You've been hanging around me too much, and you just write problems down wrong. You look at it, and it's a disease. I kind of like spread that where even if you never had that problem before, once you're in my class, you'll notice that you just copy things down wrong for no apparent reason. All right, 71 also gave a picture, and they gave a picture of a tower, and you're trying to find some things about about that. All right, so they ask you to find how far away you are from the tower and how long your wire needs to be. And how many of you knew that that wire that holds up a pole like that is called a guy wire, G-U-Y, instead of a guide wire? How many of you thought it was guide wire? I did. Okay, I'll admit. And your brother was very interested when he found out it was actually named after him. He thought that was cool. So he's got a... and we have a few on, at least we used to have a few of these on campus. I don't know if we have any anymore.
Wait, why?
Over by the baseball field, the poles that held up the netting.
Oh, yeah, they do.
Yeah, they had the wires there. And we would go out, we would measure the angle that it was creating, and then we would use that and how far it was away from the base to see how tall that pole was, and do that calculation that way. Now we're going to have to hunt for that whenever we make our little things. They have a name for it, and I'm not sure what the name is. I forget. Okay? How many of you got at least one of those right? You got both?
Yeah.
Nice. Okay. All right. So we're doing pretty good on this. All right. 72. All right. This was the height of the mountain. This was the mountain problem. Anybody think they got the mountain problem right? I'll certify you a genius right now. You think you might got it?
The which one?
I think I got all of Mr. Godfrey.
Okay, cool. That's totally fine. I didn't tell you couldn't get help.
I just show a try.
Okay, so here's the mountain problem. All right, I broke it out into two different things. Here is the first one where they are 13 plus X miles away from the mountain, the base of the mountain. Okay, and this is the angle, and that's the height. Later on when they drive, now they are X away, and the angle is bigger, but the height of the mountain is still the same. So this X and this X are the same thing, that H and that H are the same thing. Okay, does anybody understand, everybody understand how I labeled it? Okay, so I have two different problems and then they're going to come together. So the tangent of the 3.5 degrees equals h over 13 plus x. And the tangent of 9 degrees equals h over x. So I solved both of them for h. Once I solved it for h, I could then equate the two together. So we go back to what we finished up with last semester, where we use systems of equations. I had two things I didn't know. I didn't know how far I was total away from the base of the mountain, and I didn't know how high the mountain was. If I got two equations, two situations, then I could figure it out. Okay? If you don't... What's that?
I didn't know the sub equal. Why do you set them?
Because the h and the h, it's the same thing. The height in this problem is the same as the height in this problem. So that means that this has to equal that. If they both equal h, whatever that number is, then they have to equal each other. And then it becomes a fairly simple problem. It's just algebra from there to figure it out. If you don't have this written down, I would highly, highly recommend you write this down, how to do this, because you're going to see it again. Did anyone get this one now that you're seeing it? Did you? Nice. You got it too. Did you have help or did you do it on your own?
No, I don't remember how I did it.
You don't remember how you did it, but you got the answer. You got it too. Very nice. Did you have help or?
No, I didn't.
You did on your own. Wow, I've got 3 geniuses in my class. Yeah, I have not had many people get this on the first shot. There is another way to do it that we will learn about later, but I think this might be just as simple as this other way. There's another way to do it with either law of sines or law of cosines that we'll learn about next couple of classes. And that's where you don't have to have right angles to solve things. So it's a little correction factor you put on there. Yeah, so that had the picture there, but it didn't put in the little X for the extra distance that you had to go. And we'll use this same one again, the same problem again when we do law of cosines, or sines, I believe. Yeah, the sines. Okay, 73, I thought was one of the harder ones, mainly because just the way the picture is drawn is a little confusing. So did you guys get 73 and 74 are the 2 hard ones I think there. If you got what was going on with being a radius, you could make that then the hypotenuse. It was actually a very easy one. Yeah, it was actually very easy once you get it. And here is 70. Here's 73. Okay, I think this right here was the thing that most of you didn't get, right? The fact that they said that it was on an arc that was, and they gave you this, like right here, the little circle that it made going around, and they gave you this dimension here as being 56, but your hole wasn't till you got up here.
You want to slide it up just a little bit.
Yeah.
The other way, so I can see 17.
Oh, you need to see that a little bit more. Okay.
That's good.
Yep. Okay, so the key there was figuring out that your hypotenuse was 56. Let me show you the picture again, and then you can see why that's the case. There's the picture, and this whole thing right here is 56, which means every one of these lines right here is 56. Okay, I will admit that one was probably the hardest conceptually to get if you're not used to word problems and seeing little tricks like that in there. All right, so once you get that, it's not too easy, it's not too hard to figure out what to do. Use sine and cosine with 30 degrees, and then you can use sine and cosine again with 60 degrees. However, yes?
How did you get the triangles just from the points, like x1, y1, and x2, y2?
Okay, let's look at the picture again. If this is my picture, would you agree that the height right here is going to correspond to whatever y value this is? And x value this is will tell you exactly where that's located. We're assuming this is 0, 0. Okay, so I made a triangle right here. And I'm trying to figure how far up and how far over. okay? This is one of the trickier ones to see because you don't see a triangle there, you have to make one. You have to make it and realize that that's what's going on. Okay, make sense now? Okay, got another thing. Whatever I get for x here, I'm going to make a statement and then we'll think about it. Whatever I get for the x value here is going to be the y value there. Whatever I get for the y value here is going to be the x value there. Okay, let's look at why that's happening. I think you can see it better here. Alright, so here I figured I use sine of 30 degrees to figure the y value. I use cosine of 30 degrees to figure the y value. At the same time, this right here is 60 degrees, right? That's what it has to be. So this triangle and this triangle are only different in that I moved it around and the 60 is now here and the 30 is up here. So we're here, this y value is opposite when I go to the 60, or here, the opposite is the x value. So the tangent, not tangent, the sine, where I had to use sine to figure out the y value for this one, when I used sine to figure out the value here, it was the same as the cosine of the other one. The sides have to be the same. It's a 90, it's a 90, 60, 30 triangle. Both are 90, 60, 30 triangles. Both have the same hypotenuse. So the sides have to be the same. So the side opposite to 60 degrees has to always be opposite to 60 degrees. That right there has to be the same as that right there. Opposite, this is the y, that's the 30 degrees there, and that's there. So you didn't really have to do two problems. If you solve one, you just reverse the numbers for the other. Anybody get that one? That one was hard. Did y'all get that? Dang. Y'all are proving me wrong here. Okay, so this one was definitely hard. And mostly because the drawing, the angle was so small. Yeah, the angle was so small, 3 degrees. Ugh. So when I drew it, I say I'm going to draw an exaggerated picture. So I cut it down the middle and drew, instead of the 3 degrees being actually 3 degrees, I just said it was 3 degrees and made it a lot wider so then I could see what was going on. Okay? You don't have, sometimes drawing these things to scale is not good for you actually seeing what's going on. Because really all we need to do is know opposite, hypotenuse, and all of that. So when I do that, I know that's 5, which means if I go straight up here, that's 5. And what I'm going to try to find is x. So that the diameter will be x plus 5 plus another x. Now here it looks like, whoa, that's somewhere around 12 or something like that because I exaggerated how big x is. X ends up being very small. As you can see in the picture, it's a very small difference. If you're only going tapering 3 degrees. Okay, so what I need to do is find x. I know that's 15, that's 3 degrees, so I'm going to use tangent to find that, and I get x is 0.786.
Got it up to there. I just didn't realize there were two. You had to do X twice.
Yeah, okay, that's very good. You got it that far, that's good. Did you draw out this or?
No.
Yeah, and I think that's what I think, yeah, if you draw it out, exaggerated view, and that way you then see, oh yeah, 5 is this part, I've got 2 of those x's. Okay, very good. Okay, so you're getting some little strategies of how to draw these out, and when you need to draw, how much you need to draw, and all of that. Okay, next one was 75, and 75 was very similar to the one you had before, where you had the 10 centimeters and you had to find out x and y. I was hoping if you did this one you could go back and then do the one with drilling the holes, because this kind of gave you a little bit of a hint as to what was going on. How do we do on that? We get quite a few people get this one.
Which one?
75. X and Y values. And you should be able to then look at the picture and see, yeah, it makes sense that X is a lot bigger than Y. And you think about that, if you have just 10 degrees up, that's not going to span a whole lot. Okay, 76. All right, here's my balloon. And the wind is blowing it. Notice that's definitely not an 85-degree angle, but I wanted to, I exaggerated how much the wind was blowing. And then we did a whole lot of angles and saw the more the wind blows, the more, as the angle decreases, so does this side here. So as the breeze gets stronger, the angle becomes less. As the angle becomes less, the lower it is to the ground, the closer it is to the ground. So height drops. Okay, did that bother anybody, or was it just the fact that it was just kind of weirdly worded? Did you understand how the balloon was set up and everything? So the balloon's tethered right here. My wind is coming this way.